Ohm's law is, of course, our relationship between voltage, current, and resistance. And so we're going to spend some time figuring out how to work with circuits that have batteries and resistors, often finding the current, sometimes finding the voltage, sometimes finding the resistance, depending on what we're interested in. So we use Ohm's law a lot, and it's worth talking about how we set these up. So when I look at a battery, just a simple circuit with a battery and a resistor, so this is our voltage, like it might be a 9-volt battery, and then we have a resistor, say it's 100 ohms, then we can calculate the current just using V equals IR, and that's fairly straightforward. But what can get confusing is understanding what happens when we add more resistors or when we add more batteries. Before we do that, it's useful to look at what happens to the current. So our convention is, this is the positive and the negative side, our convention is that current flows from the positive. So it would be the direction that positive charges flow, even though electrons are actually what's flowing. So this is what's called the direction of conventional current. This is the direction of I, but notice in the back of your mind, if you want what's actually moving, is that the electrons are going the other way, okay? But for most of what we do, that's not going to matter. So this is the direction of the current, and the current never gets used up because charges can't accumulate anywhere. I don't have a capacitor in this circuit, and so whatever current, whatever charges leave, go across this point, have to keep going. So charges aren't what's getting used up in the resistor. We're definitely getting power there, right? Because we have power equals I times V, which using Ohm's law we can then say is I squared R or V squared over R. Any of these relationships work. So what's happening is the electrons that are moving, which of course are moving this way, or the current that's moving this way, loses potential energy. You can think of it as like going downhill. Now it doesn't gain kinetic energy like we think of when we're going downhill. So what happens is that energy gets converted into thermal energy. So this power, actually measured in watts, which would be joules per second, actually heats up the resistor. Okay, and so that's what happens in a circuit, and this is exactly how stoves work. You have a power, you have a voltage, it's more than 9 volts, it's 120 volts usually, and you have a resistor that's in the form of your burner, right? That's curled up like that. You've actually got a second prong, and so the electricity goes in and it comes back out, the current goes in, but it loses potential energy and it radiates heat. And that's how you heat up your pan as you put your pan on here and boil your water. Okay, so this is Ohm's law. The thing to notice about batteries and resistors is that batteries are a constant ideal, in the ideal case, they are a constant voltage supply. So we think of them as a constant voltage, constant delta V. It's like a hill of a certain height, which can provide any current we want. Now, in reality, there are limits to this. It can only provide so much current. A 9-volt battery can provide a couple of amps of current, and then that's all it can do, and then it's short-circuited. So you do want to make sure that, notice that as your R decreases, your current for the same battery must increase to balance this out, because we're always looking for 9 volts here. Your D-cell batteries, the 1.5 volt batteries, can provide a lot more current. They can often provide up to 9 or 10 amps of current, which means that if you just take so here's my 1.5 volt battery, plus minus, and we put a wire with very tiny resistance in here, like 1 ohm or something like that, and this is 9 volts, so we're looking at 9 amps of current. We can often heat up or burn up the wire. If you touch it right here, it's really quite warm. Okay, All right, so that's how we use Ohm's law and work with power. What we're going to do then, just like we did with capacitors, is look at networks. So we're going to look at both series and parallel, okay? So series is when we have resistors that are in a row. So this is series. And parallel are what we've seen before. Let's try to squish this in here so it fits. There's a resistor and there's a resistor, okay? So this is parallel. The thing to note about series compared to parallel, so it's the same definitions that we had for capacitors, is that in a series circuit, the current that goes in continues to flow through the circuit. So in a series circuit, the current is the same through the resistors. This might be R1 and R2, but the voltage is different. The voltage drop is different if they are different resistances. For the parallel case, so this should feel like some of what we were doing with capacitors. We identified what was the same and what was different. For the parallel case, then both of these can be seen as basically having their own connection to the battery. Like this one can see the top, this can see both the top and the bottom of the battery. So in this case, the delta V is the same. If this is a 9-volt battery, then we have 9 volts across this and 9 volts across this. The current is going to be different. It's like each one has its own arm connected to the battery, and they're each pulling their own current to light up. So this, if this is a light bulb and this is a hairdryer, they're pulling different amounts of current, but they've got the same amount of voltage across them. And these are called loads, right? This R1 and R2, or we can talk about a resistive load. And so as we look at this, what's useful is to, again, think about what gets used up and what doesn't. So in this case, the current that goes up and around has to be the same, right? It can't go anywhere. But in this case, I have current, right? Current that goes in and it splits. We get, let's say, maybe that's the total current. Part of it goes through R1 and part of it goes through R2. And so we say the current into this spot equals the current out. So one of our rules in looking at circuits is that current in to any spot is equal to current out, because it can't accumulate unless we have a capacitor and then we can build up charge somewhere. But for simple resistive circuits, current in equals current out. And the other rule, so this just says we can't build things up. The other rule is that the change in voltage anywhere around the circuit, if you get back to the same point, so the change in voltage from, if you go around the circuit and come back, is equal to 0. That means if I start here and I increase the voltage by 9 volts, then by the time I come back around, I must have, so if this is a positive 9 volts, then by the time I go through these two resistors, that needs to be a negative 9 volts, so that by the time I come back here, my voltage change is 0. In other words, it's an energy conservation. If I increase my energy here, I must decrease it by the same amount going around the circuit. So this is energy conservation. And so this is another way to see, hey, if I go around the circuit, if I start here and I go up by 9 volts and I take this path through the first one, then this I1, then I've got 9 volts that I must drop across here. But if I go and take this path over on this side, then I must drop 9 volts on this second arm right here. So they do have the same voltage drop. We have different currents. So we're going to use these pieces then to set up how we can work with resistors in parallel and in series, this idea of equivalent resistance, just like we did with the capacitor.